written as ny is greater than 1 plus nx. So we realize is, well, what I have to do is I have to find bounds for this nx for this to work out. Does that make sense? So what he does is he says, well, let m1 and m2, I'm using his notation in Z, be positive. So let's just say in n, be such that m1 is greater than nx and m2 is greater than minus nx. So how did he do this? He did the Archimedean principle with 1 as your positive number, and nx being the number you want it to get bigger than, and minus nx being the number you want it to get bigger than. Does that make sense? You see how this is the Archimedean? I mean, I'm going a little fast only because I'm running out of time. But this is by this is by A again. And I want you to think about this. This is a good thought process. But what he did is he said by A, where x equals 1 and y equals nx for the first one and y equals minus nx for the second. He says I can find a multiple of 1 that's bigger than nx. I can find a multiple of 1 that's bigger than minus nx. Does that make sense? That's how we got these two numbers. But putting these together, this tells me nx is between two integers. Does that make sense? But the beauty of this is now you're saying, look, nx is between two integers. We know that the integers have this property that if you take a set, it has a maximal element. It doesn't just have a supremum, but it's in the set. There's the biggest element in the set. So you take all the integers less than nx, and you find something that's here, and then you take, does that make sense? I'm just kind of running through this because we're running out of time. Are you guys with me? Let's stop here. Are you guys with me? Yeah.
So like, so looking at like what we're trying to do, if x and y, so x and y here are real, right?
Yes. Any real numbers, they can be both rational even, it doesn't matter. But the important thing is these aren't equal signs. So for there's always a rational between two rationals. I mean, you just average them and you get it. What I'm trying to say is, okay, so you agree, this is between two integers. So that means I can find an integer, the biggest integer that's less than this. Yeah? Agreed? I mean, I look at all the integers that are less than this. Yeah?
Sorry, I'm going backwards too.
That's fine.
Okay, so
I'm going to probably end with this proof. Maybe I'll state the theorem, but I'll just start with that tomorrow. Yeah?
where I get stuck is, okay, say on A we call Y like gamma or something.
Sure.
So then we're looking at gamma equals
This
0 at
nx.
the beginning, then it becomes 1. The next
Right, so I should be careful with these x and y's. If they were like alpha and beta in part A, this is the positive number that I want to try to take a multiple of to get big. And this is that's what you're calling gamma, let's say.
Yeah, how did we go from y minus x is greater than 0 to n y minus x is greater than 1 when we're talking about n?
Which one? Sorry, which one?
By A,
Yeah.
0 became 1. And I was just
Right, so I'm going to say A is 1. I'm going to try to take I'm going to try to take a multiple of 1 that's bigger than n times x.
So it's arbitrary.
That's right, but it's by the Archimedean principle we know we can.
Okay.
Does that make sense? I'm just going to keep looking at multiples of 1 integer. Eventually I'm going to pass it up.
Okay.
And then I'm going to do that with negative x as well, and eventually I'm going to pass it up. And that gives me this sandwich. So now I know that there's integers less than it, and I now know there's integers more than it. Does that make sense? So what it means is I have all these stupid integers, all these points on my real line going that way. Now I'm going to take the first point, the point closest to it, the biggest point before it. And then I'm going to look at all the points going after it, and I'm going to take the smallest. And those two are going to sandwich nx like this. So that means we can do this. So I'm saying it in words instead of writing it down because I don't know a good way to write it down. But yeah,
How exactly can we show that we know we can do this?
how we can do this?
The next step, what we just did.
Oh, well, right, so this is him assuming you know everything about the integers in Q. But the integers are something called well-ordered. So it's stronger, in a sense stronger than the least upper bound property, because not only do they all have least upper bounds, but they're contained in the set. Right, the integers, if you take any set of integers that's bounded above, there's a largest integer. And if you take any set of integers that's bounded below, there's a smallest integer. So he took the set of integers less than this, it's bounded above, it has the largest integer in the set. Does that make sense? So it's like it's the next level of the least upper bound property, but it's not as useful because when you're well ordered, there's holes between every step. Does that make sense? Because you can take any element, the set of all things bigger than it, there's a smallest thing, there's a hole between it. Does that sort of make sense? So you can do it. I didn't go into it because if you wanted to go into it, I could teach you a week about like well-ordered and set theory and all this stuff. But it's just not worth my time. It's not worth your time. Not for the sake of what we want to go with this course. But do you guys agree I can do this? I can find the biggest integer smaller than it and the smallest integer bigger than it. And those will be 1 apart. No matter where this is. I'm allowing one of these to be less than or equal. But because if this is an integer, then things are fine. But does that make sense? So now we stuff things. So now the beauty of this is now look, what is this? This translates to m is less than or equal to nx plus 1. And it also tells me nx is less than m, and m is less than nx plus 1. Because I just add 1 to this inequality. Yep? So now I have to put everything together, and this is where I always get confused. Where did I have? Oh, I had this inequality. So what do we have? Well, we have nx is less than or equal to m, which is less than or equal to nx plus 1, which is less than y, by using this guy. Just basically throwing him in there. Agreed? Now do you want to see the trick? Ignore this. Now, oh, sorry, not y, sorry, ny. Ignore this, and now you have nx is, I need to get this, oh, this is strictly less, right? You want to do this. Sorry, you want to make sure this is strictly less. This is strictly less. Because you just choose the integer to be, if it's an integer, just make that m minus 1 and pick the bigger one. Nx is strictly less, so this is strictly less. So now you have m between nx and ny, divide all the inequalities by n. And this gives you that the m over n is between x and y. And that's your rational number. So I know this is confusing as hell. That's how these proofs often are. But if you step back and think of what he's doing, it makes perfect sense. First, he's finding a 1 over n that's smaller than the step size between x and y. So that he knows when I take a large enough multiple of this, I eventually have to fall in there. Make sense? And then he's telling you what, because this is what Rudin does. Rudin is like, I'm pretty sure he's really OCD. I mean, I never met the man. But like he's, instead of just saying, this makes sense, we can do this, he's actually finding the numerator necessary to do it. Does that make sense? But he's just saying, look, like he's trying to find the numerator for it by just saying, find an integer such that it's less than nx. Like 1 less than is less than nx, and 1 more is more than nx, and that must be the integer we're looking for. Does that make sense? I know this is confusing. But this works. Can we agree on that, or is this just too much and everyone wants to just walk away right now? I mean, I'll let everyone go if you guys think that this is enough for one day. But if you guys want, we'll keep talking. Or I could ask if you guys have a question. Think about it for a second. Well, I have 8 minutes. I was going to do one more thing, but if you guys, like, if this just blew your mind and you want to just think about this, I'd be willing to stop now. Maybe just take questions, or we can sit around working on the worksheet, or we can just see you tomorrow, whatever you want. Guys? Yeah. Yeah. Right, so what I'm saying is, look, apply A with the positive number being 1 and the other number being nx. So you'll get that some multiple of 1 is bigger than nx. Some integer is bigger than nx. So now apply the same thing with your positive number being 1 and your other number being minus nx. So some integer is also bigger than minus nx. Does that make sense? So what I'm doing is I'm just applying A a lot of times to prove this. It doesn't, I mean, he does this explicitly, and I'm trying to walk you through it so you understand why it makes sense, but also what he's doing. The thing is, it's not always, that's one of the issues with, in general analysis, is that sometimes you just sit down and do these awful computations and it works. But the most important thing you can do after this long, awful computation is step back and be like, what did I do and why did it work? And what I'm telling you is what he's doing is finding a step size that's small, and then finding the first step that gets past x. Right? This is the first step that passes x. That's why he's choosing m minus 1 to m. He says before it wasn't past x, after it has to be past x, and he's saying because 1 over n is smaller than the step size, that is past x, but it can't be past y. Does that make sense? Again, if you look at the